It doesn't glow green. It doesn't explode on its own. You can walk past it and never even know it's there. But this substance holds the power to wipe cities off the map, or keep them lit for decades. It's the core of nuclear power and the soul of the deadliest weapons ever built. Nations have gone to war over it. Scientists have dedicated lifetimes to understanding it. Spies risk their lives to steal it, and only a handful of facilities on Earth know how to make it. Enriched uranium. It's not mined, it's engineered, atom by atom, isotope by isotope, under layers of chemistry, physics, and security so intense, even many nuclear engineers are denied access to the process. It begins as ordinary rock and ends with the most dangerous material humanity has ever created. This is how enriched uranium is made. Part 1. Digging up a nuclear future. It starts in the Earth, buried deep beneath layers of stone, sand, and time. Uranium ore is a naturally occurring mineral found in deposits across countries like Canada, Kazakhstan, Australia, and parts of Africa. Miners use massive excavators, explosives, and ventilation systems to access the ore, pulling up rock that contains only small amounts of uranium, sometimes as little as 0.1% by weight. But the most important isotope in that ore, the one that makes fission possible, is uranium-235. And it's barely there. Out of every 1,000 atoms, only 7 are U-235. The rest is uranium-238, which can't sustain a chain reaction. The ore is crushed into powder and treated chemically, usually with sulfuric acid or alkaline solutions, depending on the type of rock. This separates the uranium from the waste rock, producing a concentrated substance called yellowcake, a bright yellow powder with the consistency of flour. It's not yet dangerous, it's not yet useful, but it's the first sign that this rock will someday split atoms. Part 2. Converting solid rock into deadly gas. Yellowcake is uranium oxide, U3O8, a stable compound that's chemically inert. But to enrich uranium, you can't work with solids. The next step is chemical transformation, turning yellowcake into a gas called uranium hexafluoride, UF6. This is done at highly specialized facilities through a process that involves reacting yellowcake with hydrogen fluoride and fluorine gas. The resulting substance is a white crystalline solid at room temperature, but when slightly heated, it turns into a highly reactive gas. UF6 is dangerous. It reacts violently with water, even the moisture in the air or in your lungs. The facilities that handle it are sealed, automated, and reinforced to contain every molecule. The gas is loaded into heavy cylinders, each one marked, tagged, and monitored, and prepared for the most complex part of the journey: isotope separation. Part 3. Spinning atoms in the dark now. The real science begins. Because U-235 and U-238 are chemically identical, traditional chemistry can't separate them. But there is one crucial difference: mass. U-235 is just slightly lighter than U-238, about 1% lighter, and that tiny difference becomes the basis for one of the most remarkable industrial processes on Earth. Inside tall, cylindrical machines called gas centrifuges, UF6 gas is spun at incredible speeds, up to 100,000 revolutions per minute. That's faster than a jet engine turbine. The centrifugal force pushes heavier U-238 molecules outward, while lighter U-235 molecules collect near the center. But here's the catch. The separation is tiny, less than 1% per centrifuge. That's why enrichment requires cascades, hundreds or even thousands of centrifuges all connected in series. Each one slightly increases the U-235 concentration step by step until it reaches the desired level. This part of the process is shrouded in secrecy. the arrangement of cascades, the speed of rotation, even the material used in the centrifuge rotors. These are all classified because controlling this stage means controlling the ability to make nuclear fuel or nuclear weapons. Part 4. Fuel for cities, or for bombs. Once enriched, uranium has two futures. For civilian nuclear reactors, the goal is low-enriched uranium, LEU, usually around 3 to 5% U-235. This is stable enough for controlled fission where energy is released slowly to produce steam and electricity. The enriched UF6 gas is cooled and turned back into solid form, then converted into uranium dioxide UO2 powder. This powder is pressed into small ceramic pellets, each about the size of a pencil eraser but capable of powering a home for years. The pellets are baked at over 1,700 degrees Celsius and loaded into fuel rods, long tubes of corrosion-resistant zirconium alloy. But for a nuclear weapon, the uranium must be enriched far beyond 5%. Weapons-grade uranium contains over 90% U-235. Reaching this level is extremely difficult. It requires extended enrichment in ultra-secure centrifuge cascades. The gas is processed repeatedly until the U-235 concentration is high enough to sustain an immediate, massive, and uncontrolled chain reaction. Only a handful of countries possess this capability, and every step, from cylinder weights to centrifuge speeds, is watched by international inspectors and surveillance systems, because a few kilograms of HEU handled improperly can change the course of history. Part 5. Security, secrecy, and surveillance. Every gram of enriched uranium is tracked. Every facility is monitored. Transporting enriched uranium, whether for fuel or research, is a logistical and security nightmare. It moves in specialized shielded casks, under military escort, often across continents by armored train, plane, or truck. Inside enrichment facilities, security is multi-layered: biometric locks, 24/7 armed guards, surveillance drones, and radiation sensors. Only a select few workers ever interact directly with the uranium, and even then, only through thick glass or robotic systems. Tampering, theft, or deviation from protocol can trigger an international response. That's how seriously the world takes this material. Because enriched uranium can light cities, it can also end them. Part 6. Power and paradox. Enriched uranium is one of the greatest paradoxes of the modern world. In the right reactor, it provides decades of clean energy with zero carbon emissions. A single fuel rod can replace thousands of tons of coal, but in the wrong hands, it becomes the deadliest force known to man. The science behind it is brilliant. The risk it carries is enormous, and the decisions that govern it, who gets it, how much, and for what purpose, are among the most politically charged on Earth. Making enriched uranium isn't just a matter of chemistry and physics, it's a matter of trust, of strategy, of global survival, from deep earth mines to towering centrifuges, from yellow powder to invisible gas, from energy to annihilation. Enriched uranium sits at the very edge of human capability. It's the most advanced process science has achieved, and the most dangerous line politics has ever drawn. This is how we split the atom. This is how we bend it to our will. And this is how enriched uranium is made.